Okay, so 2.4 begins on page 92. The title of it, I don't think I would call it this. I would call it an introduction to proof using algebraic reasoning. It's called algebraic reasoning, but the reason we have got this section in the book is because it's kind of a bridge between things you're familiar with, so you don't have to put a lot of mental effort into the algebra that's involved. You can focus on what the proof is doing, so that we don't throw new geometry and proof at you at the same time. That's kind of an overload for your brain. So we're going to depend on, and I hope this is true, we're going to depend on your skills at doing algebra. That should come easily to your mind and not occupy a lot of space, so that you can focus on how the algebra follows through and has specific reasons for why we what we do, and we have to write those reasons. Anyway, I want to remind you of where we've been, and I want you to put these things on a piece of paper so they're all in one place, rather than scattered throughout your notes, or maybe you didn't take any notes at all, or even scattered throughout your book. I want all of these things I'm about to tell you and show you in one place. And at the top of it, you should probably put postulates, theorems, and definitions. That should be the title of your paper. Postulates, theorems, and definitions. And I would dedicate a page to it, maybe several pages before you're done. So maybe put it in the back of your notebook and give it 5 or 6 pages. Postulates, theorems, and definitions, which you're going to need. And so what I'm going to do is I'm going to tell you how we're going to abbreviate things in a proof. I'm going to tell you what it means. So hopefully when you see it next time, you can look through this list you're making and go, oh, that looks like this. I bet you this is the answer. First one is called segment addition. And we are going to abbreviate it this way. If you can't remember what that means, then write it out on your paper. Write the words segment addition. This is the abbreviation for it that we will use in our proofs, or at least I will use in my proofs. If you can't remember what the actual abbreviations are, you won't get marked wrong if you write the whole word segment addition out. That's fine. But this is what I'm going to allow you to use for an abbreviation if you like. And it's a conditional statement. And it says this. It refers to a segment, of course, segment addition, that is split up into 3 pieces, where we say that B is between A and C, and it can only be between A and C if it's also on the segment with A and C, okay? So B is between A and C. If we have this situation, here's what we can say. It says if B is between, and we mean on the same line, that's what the word means, A and C, as we see in the picture, then, so it's a conditional statement, then AB plus BC is equal to AC. Okay? This is actually a definition, although it doesn't say definition up here. This is generally the way that it's used in this direction. But it's also true that if AB plus BC equals AC, then we know that B is between it. When I was in high school, this wasn't segment addition. It was called the definition of between. But we will call it segment addition because you're actually adding 2 segments to get a longer segment. It's not a very difficult concept, right? Better not be. From the picture, you can see that this segment plus this one equals the whole thing. Yeah? Okay. The next one is angle addition, and it's the very same kind of thing. Angle addition, and that's the abbreviation. If you don't know what that means or you can't remember, then write out the words for yourself on your paper. And it has a picture like this, where we're going to add some angles. Like that, for example. Are adjacent. So if they are adjacent, then in this case, with respect is the midpoint. If you are told that Q is the midpoint, then you are. So give ourselves a segment. Call it, call it AB. And we'll have a bisector coming through here like this. Call it N. This one over here is right here is gray right there. B only if these two angles are equal. So if you're this one, you can assume that the thing that split that big angle in half, creating those two equal halves, is a bisector. An angle. You use it, you got it all in one place and can see things. Okay. Next one. That's our abbreviation for that. And this one, it does need a picture, but they don't have to be connected. So for example, I might have one angle like this and another angle like this, completely separate from it. They're not connected at all. They kind of look like they could be if we close them together, and we'd probably form a right angle there, but that's not what's going on. It's not a right angle. There's two separate angles, but this is what we say. Angle 1 and angle 2 be added up to 180, but not necessarily connected. They could be, they don't have to be. So we have a picture. Still, they have to add up to 180. This one isn't a definition. It's an observation. So here's the way it might look in your proof. If you're doing geometry things, which is what we're going to use it on most. For example, if I know somewhere in my proof, if I have this fact that AB equals PQ, then I could, if I wanted to, write this. The reason we would have for it is by addition, because we cannot abbreviate subtraction this way. Because we also, well, AB equals my addition is MULT. That's our make sense or not? Huh? Yeah. Yeah. Okay. Apply when we're adding, multiplying, and dividing with these things having to do with geometry. Give an example. If, for example, here that are equal to the same thing are equal to each other, and the reason is substitution. That's the most common use of substitution. There are others, and as they arise, I will show you and make a big deal of it. Because substitution, that's probably the most common reason we have for things. Substitution is a big deal. I have one other for you. Two others, actually, that are algebraic, like these were, that I'm erasing. And this happens very seldom. It'll probably happen today fairly often, but it won't happen again. But we may need it later.
Can I get the assignment?
Yeah, you can try it. Good luck. The rest of you can write it down right now too if you want. I know you've been writing like crazy, so write something else. This is just distributed property. And then one more. And you won't find this one in your book anywhere. They want to call it, your algebra teacher said that, plus 7y, not y. Then in your next line, if you want to write this, you would say 10x minus 2. Getting from here to here is because you combine like terms. And you would put CLT for the reason. You know what I mean? Okay. That's about all we know up to this point. We have discussed some others, but as they come up in geometry, I will make a big deal about them. We'll put them on this page. So keep this page someplace where you can access it, because you're going to continue to add things throughout geometry. Look how many things. We are that's what I've introduced to you today. So you want to keep that paper handy, so you can keep everything together in one place. Okay, so we've got enough to do. Oh, we're going to erase this, and we're going to do an actual proof for the first time. I cannot stress enough how you use the space to do a proof so that you're not cramming things together. Cramming things together also crams it in your mind, and it just does not work out. So when you do an entire assignment of proofs, you need a great big T. We call them on without crowding. So when you come up to get help from me and you've got your proof in this little tiny corner in the bottom of the page and I can't read it, I'm going to make you go rewrite it bigger so that we can discuss it and see it. Okay, so let's see what they got for us here. First one says to solve this equation and justify each step. In other words, our first proof is going to be this. This is what we start with. This is how a proof looks. Now, remember I just said every proof is going to have a picture? These won't, because there's no geometry here. It's algebra. And so they have a picture to accompany every proof drawn on your paper. Not in your book, on your paper, with the proof. Okay, but not for these today. So here's how you start. You start out with what they gave you. One then is going to be to write down what they gave you, which is 3x plus 2 equals 23 minus 4x. Now you guys, we'll do that. We'll add 4x to both sides, and you will write 7x plus 2 equals 23. You will not write this stuff that you've been writing. And what would be the result of doing that? 7x equals 21. And the reason is subtraction. Make sure you go clear out to TR or at least T, not just SUB. Don't use that. What would you do next in the solution of this? Divide by the 7, and the result would be x equals 3. So how did we get from here to here? We used division. So that wasn't that bad, right? What we've done is we've taken an equation and we use the skills you have in algebra so that we're not suffering with the solving. We all know how to solve this, or you should. Now to get from here to here, that's not what we're after. We're after you being able to provide a reason for each result as we go along. Yes.
Why does it say given?
Given, because you got to have something to start with.
Oh,
This is the problem that they're handing you, and every single step in a proof has to have a reason, and the first one is always what's given. This is what we're starting with, and the book or the author of the book or me or whatever, this is what I'm handing you to work with. Now, so the given means I'm giving you this. Now work with it. Okay, so the first reason will always be given. Okay, take a look at example 2. We got another T proof here. Looks like this, so that you can kind of get used to it. And number 1 is going to be the equation that they got for us, and we are going to write given next to it because that's what they're handing us. And it is -5. Whoops. -5 times 7W. Just get it nearly as slow as I did on that one. So number 1 reason is this is what they gave you to work with, given. Number 2, I would write -35W minus 40 equals 30. And what happened from here to here is distributed. Then I would do this. I would write this result next, which would be -35W equals 70. Addition. Good. Very good. And then I would write division. So it's not so bad, right? At least today. When we start doing the geometry proofs, it's going to get a little rough. I don't think we're going to do number 3. We're going to stick with this kind of stuff here. Okay. Now we're going to do one more example. I think there's 2 more examples. I don't know if we're going to do. We might talk about example 5, but example 4. That's where we say, metaphorically, this is where the rubber meets the road, because this is going to do our first geometric proof with the geometry and the segments and the angles, not variables like what you're used to. So watch how this goes. This is pretty, and don't be too upset with yourself if you don't get it first time through. I'm going to try to talk you into it. Example 4 says, you reflect the beam of a spotlight off and determine whether, okay, and you know what? They're trying to make it real. I don't want you to make it real right now. I don't want you to try to put anything in context. We got enough to think about as it is. Here's what we've got. We've got a diagram like this, and this is what I mean by drawing a picture if it's geometrically oriented. I got an angle coming out here and one coming out. Draw these, folks. It takes quite a lot to put a proof together before you can even start thinking and doing it. So plan on some prep time for each. Well, they tell us. It says determine. Sorry. They do put back to this picture and over your proof and back to this picture. So if you want to augment the picture for your own purposes, go ahead. It still has to have the same given stuff. But if they don't have things numbered and you'd like them to be, please do that. Put it in your picture. So this is given. And this is different from the algebra proofs that we did because we knew how to solve it when we were done and we said x equals, we knew we were done. Now there's one more element you've got to add to this, and that's what you're trying to prove. So you put that up on top up here so you can keep that in front of your eyes all the time. We are trying to prove in this situation, if you look carefully, we're trying to prove that DBA is equal to angle. This is what we're out to prove. That's what it says at the bottom of the words. Angle EBC. Notice that they have little m's in front of that. It means the measure of. We will just leave those off. You can just read right over the top of those. We're trying to prove that angle DBA is the same size as angle EBC. Okay, it's going to be a little rough. Try to stay with me. And I don't expect you to come up with this proof on your own, this kind of proof, until you've seen 1 or 2, which I'm showing you now. That's a big guy. That's an obtuse angle. We know that these 2 acute angles are equal. We know those little dudes are equal. But DBA is bigger than these given things by angle 2. It's bigger. We got angle 3. We know something about angle 3. It's in the given. But what we're trying to prove is something about this angle over here. And this angle I'm trying to prove something about is bigger than what was given by angle 2. So watch what I'm going to write next and see if you agree, even though you may not be able to come up with it on your own. I'm going to say angle 2 plus angle 3 equals angle dBA. Right? Does that look right? Let me tell you why I'm writing this. Because you can't prove anything about angle dBA unless you can get it into the proof somewhere in an equation. Angle and segment addition. Those are the first things I talked to you about. Angle and segment addition are called the great bringer inners. Angle addition and segment addition allow you to mention things that you're trying to prove something about that haven't been mentioned yet. They let you bring things in. So to mention dBA, I'll have to look at dBA and say, okay, dBA, that's bigger than what I was given. I was given angle 1 and angle 3, these two little dudes here, but I'm supposed to prove something about dBA in my proof yet, but I'm going to have to prove something about it. I want EBC in here now.
Angle 2 plus angle 1 equals angle EBC.
Angle what? EBC. And notice that I did not put a 3 here. Because both of these are saying the same type of thing for the same reason. And when we have a little angle plus another little angle next to it that equals a big angle, that is the heart and soul of angle addition. I've added 2 littles to get a big twice. So they're on 2 different lines in EBC. Here's my problem. Now get this. First say that these 2 red boxes are equal to each other.
So can we do something with the top thing? Because it's like angle 1 equals angle 3.
Yes. Aren't those things in the red box? I may have them in a different order, but aren't those the things in the red box? Isn't it these 2 things that I need to be equal? And you're exactly right. I can say these are equal based on this, because look at this equation right here. This is understood to be true. This is a fact. How could I use this to be able to write this?
We subtract them. Yeah, subtract angle 1 from angle 3.
But hang on just a minute. These guys right here, angle 1 equals angle 3. There it is. There's angle 1 right there. There's angle 3 right there. What have I done to this to write this? We added angle 2 to both sides. What do you call it when you add the same thing to both sides of an equation? Addition. If you have a fact and you take that equation, you add the same thing to both sides, which is what's happened here. That's addition. It's addition. It's an algebraic property. This was an equation. I added the same thing to both sides of that equation. That's an application of addition. And sure enough, this guy right here and this guy right here, they're in the red boxes, and I've just said they're equal. Not because this was equal to this. I can't assume that because that's what I'm trying to prove. But I got that this was equal to this based on what was given and adding the same thing to both sides. And it turns out that's what I needed. Since I've said that this red box equals this red box, I can now say that angle dBA is equal to angle EBC. How come? What do you think the reason is?
Because the red boxes are equal to each other.
Is that what you're going to write here? Because the red boxes are equal to each other. What are you going to write right here? Look, 2 things. These 2 thingies. If these 2 things are equal, and they are, then the things they're equal to are equal. If 2 things are equal to, if these 2 things are equal to the same thing, you're going, but they're not the same thing. Oh, yes, they are. Look, they are the same thing right there in this step. These 2 things are the same. That's what equals means. So I have 2 things, dBA and EBC. I have 2 things that are equal to the same thing. These are the same thing. So they are equal to each other. Substitution. Done. When you have written what you're trying to prove, you know the problem's over. Some of you will find this very difficult to figure out. Some of you out there, I'm seeing you already, and you're nodding and you're going, yep, I see it. Some of you don't see it yet, and it will be a struggle for you. But if you keep fighting the fight, I will bring you along until you can do these. They're hard for a lot of people. My experience has been about 10% of my geometry students latch onto this, and they think it's the greatest thing they've ever seen because it follows in their mind. They're very logical thinkers. It's just the way they are. Most people, 85, 90% of the people have a tough time with this sort of logic. But if you keep fighting the fight and not give up, we'll get you there. It takes a little effort. Okay. Let's take a look for just a second at example 5. I'm not sure that it's a proof. It might be. Let's take a look at example 5 in the book. I may not put this one on the board. I want to leave this one up here. You may want to get a picture of this before you go. These main ideas here are going to happen over and over in different situations. Anyway, example 5 says, a park, a shoe store, a pizza shop, and a movie theater are located in order on a city street. Between the park and the shoe store is the same as the distance between the pizza shop and the movie theater. Show that the distance between the park and the pizza shop is the same as the distance between the shoe store and the movie theater. That is a mouthful. Holy crap, that's a mouthful. So let's see if we can understand what they're trying to say. And drawing a diagram and putting things on there is going to be useful to you. So they're all together on a street. Here's the street. We got 4 things on it, but they're not all evenly spaced. The first thing on it, it says in order, is a park. So this is the park. Then we have a shoe store, a pizza shop, and a movie theater. So I'm going to put the shoe store here, a pizza shop, and a movie theater. I do? Okay, pizza shop. I'll put a Z here for pizza. That's the only one with a Z in it. Okay, that's the pizza shop. So this is the park, shoe store, pizza shop. I know that looks funny, and the movie theater. Okay, and they're all together on a street in that order. Now let's see if we can see what they're trying to tell us. It says the distance between the park and the shoe store, that's this distance, and if you look at the words, is the same as the distance from the pizza shop to the movie theater. So these 2 segments are equal. So we mark them. That's given information. That distance is equal. It says show that. That means this is what we want to prove is coming up. Show that the distance between the park and the pizza shop is the same as the distance from the shoe store to the movie theater. That's what we want to show. Do you understand? I don't know if you do, but I hope you understand that is very similar to what's going on here. We've got 2 little ones we know are equal. We're going to have to add the same big one, SZ, to get this to equal this. It's the same sort of a notion. So if we do a proof, I wasn't going to do this, but if we do a proof so that you can see how it goes with segments, we're trying to prove that PZ equals SM. We are given that PS equals ZM. We are given that little equals little. We're trying to prove that a bigger one equals a bigger one. I'm going to use the very same sort of thinking as we did here. We haven't even seen PZ or SM in our proof, so we need to get them in there next, in my opinion. We got to get them mentioned. So I'm going to say that PS, which I'm given here, plus this extra piece, SZ, has to equal PZ because of segment addition. Do you see that? You see it or not? Yeah? So what's going to go with this in the same step?
So angle MZ equals MZ plus
MZ, okay.
SZ equals SM.
Equals SM. And here's what I want you to notice, that this segment addition and angle addition are wonderful things. Look, I've taken what I was given, PS and MZ. You said ZM, MZ, and ZM are the same. I've taken PS and MZ, and they're in here. I've added something to it and was able to mention the thing I'm trying to prove something about. Anyway, in the next step, I would use addition to add SZ to both of these, and then substitution to get this equal to this. Just like I did here. Okay? Anyway, do your best. take a lot of space. If you use 3 or 4 pages on this, more power to you. Do not cram things together. It's not like any math you've ever done. What? If it's done, but I'd really rather you take it till Monday until we go over it. We'll go over 2-3 and 2-4 on Monday. Try to have a good weekend in spite of this. See ya.
Thank you.
You bet. So, oh, you can put your back, okay. Okay, all right. So since this is still streaming and everybody's left, go ahead. I just wanted to finish this. This is just like what we had over here, only I'm doing it with segments. I have a little segment PS, and if I add it to SZ, then I'm able to say that that's equal to PZ, and that gets this into the proof. Same thing over here, ZM, MZ or ZM, plus SZ. So ZM, this one, plus this one here, equals the big one, SM, so I'm able to mention that at the end here. But I can't say that this one is equal to this, which is what I want to do, until I have established that this side, crazy marker, I can't say that PZ equals SM until I can say that this box is equal to this one. So that's what I say in step 3. Using this equation here, I've said PS equals MZ, PS equals MZ right here. And what I've done is added SZ to both sides of it. That's addition. So if this red box equals this red box, which is the same as these two, if these two are equal, these two have to be by substitution, just like it was over there with the angles. Anyway, good luck with the assignment. Bye. But